Here we have the kinetic molecular theory. We're talking about gas laws, and kinetic...
Motion. Kinetic means motion. Yeah.
Molecular...
mean molecules.
Theory.
Hey, moving molecule theory.
Moving molecule theory. Oh, there goes a molecule. It's moving.
Woo.
Oh, there goes another one. We've got molecules moving everywhere. We have 5 pillars of the kinetic molecular theory that you need to know.
Pillars, so-called, support the kinetic molecular theory. They're really the basis of the whole theory.
That they do, Jim. And you need to know how to describe these pillars. First one is tiny particles. Gases consist of tiny particles. Did you know that? Atoms and molecules are tiny?
Yeah, tiny. Like the tiny toilet in Despicable Me.
Ooh,
Curse you, tiny toilet!
It's a tiny toilet. Diameter of a carbon atom is about 1/10,000,000th of an atom.
Yeah,
of a meter.
Really small. 1/10,000,000th of a meter. Really, really small.
That's like a nanometer. Less than a nanometer.
Yeah.
Less than a nanometer. So there's the first pillar of kinetic molecular theory. The second one is that gases have no volume. That doesn't make any sense.
Yeah, that doesn't make any sense because they do have volume. What are you talking about?
They do have volume. They take up space, but gases are really spread out. They're different than solids and liquids. And because they're so spread out, their volume is insignificant. We look at that box there. You've got a bunch of little atoms, but that box is mostly empty space. So we just say, wipe our hands of it and say, all right, there is no volume. The atoms take up no volume.
Yeah, and you should be happy about this because this makes life easier for you.
Because the math is a lot easier if you say that the atoms don't take up space. They do, but it's insignificant. So they're insignificant. Very similar. They are not attracted to each other.
Yeah, a lot of times in solids and liquids, the particles actually attract each other, and that's what keeps them in that state. So when liquids lose their attraction, they start to become gases. So we assume that there is absolutely no attraction in the gas particles.
And it's really because they're so spread out that they're not close enough to be attracted to each other. So we say there is absolutely no attraction, and that, again, makes life easy because the math is going to be a whole lot easier. So they're really small. They don't take up any space. They're not attracted to each other. The big ones we have to worry about are pressure and temperature. Pressure is my personal favorite. Thing about gases is they're always moving. They're in constant random motion. And what is pressure? Pressure has to do with how they collide with each other.
So more collisions essentially means more pressure, and less collisions means less pressure. So what I like to do is a little thought experiment. So bear with me as we go on a little journey of the mind. Close your eyes, and well, maybe you don't need to close your eyes, but imagine your eyes are closed.
We want you to see the notes.
Yeah, that's true. Yeah, good point. So imagine you're in your chemistry classroom. You're there by yourself, and you close your eyes and start walking around. Well, eventually you start walking around, you're going to run into the walls of the classroom because you can't see where you're going. You running into the walls creates pressure on the walls of the classroom. Now let's say 100 people are in the classroom, all with their eyes closed, all walking around in random motion. Well, they're all going to start hitting the walls, and they're going to hit the walls more frequently than you were by yourself. So more people hitting the walls more often means more pressure.
That's a lot of people in the room. 100 people, that'd be a lot of
probably
pressure on the
exceeding
walls.
the Occupational Health and Safety Administration, or whatever it is, limits.
Units of pressure. Okay, we've got some numbers and some math now. Some of these units might look familiar. Pressure is measured in atmospheres, torr, millimeters of mercury. I've heard of that before. Inches of mercury, if you've watched the Weather Channel.
Jim Ganal, my favorite.
PSI, what is that?
Pounds per square inch. Also sometimes abbreviated as LB/IN.
Inches squared. That's actually what's on my tires when I fill up my bike tires.
Indeed. And basketballs.
And basketballs, pounds per square inch. That's okay. So we're familiar with that. KPA is kilopascals.
Actually, the SI unit of pressure, but we're not going to deal with it a whole lot.
It's kind of odd. And regular pascals without the kilo. Yeah. We can use these. They're all equivalent to do conversions with dimensional analysis. For instance, very quickly, since you're great at dimensional analysis, 352 millimeters of mercury. If I needed to convert that to PSI, I would start with the number I'm given, we set up a T-chart, and then we need to start converting. So how do I use this chart here?
Well, as you know, you use your T-chart to convert from one unit to another, so we have the unit we're starting with, and those units need to be canceled out. So those units we'll put on the bottom of the T-chart, the next part of the T-chart. So we're going to use 760 millimeters of mercury and 14.7 psi because we're converting from millimeters of mercury to psi. So notice there's something in between there. Is that thing in between, the 30 inches of mercury, do we need to worry about that?
I don't think so, because they're all equal to each other, so I
Yes.
can completely ignore that and just look at the two that I'm concerned with.
So then what we're going to do is put our 760 millimeters of mercury on the bottom, 14.7 psi in the top. Millimeters of mercury cancel each other out, and we do the simple math and come up with 6.29 psi.
Ooh, I noticed you rounded to the correct number of significant figures.
Indeed.
3.
And I used units.
Oh, that'll get you full credit on one of my papers.
That's right.
All right, so simple math. Very important. You do not need to memorize these numbers. They are on the back of your periodic table, and we're going to give you a handout to put in your journal. So ask for that if we haven't given it to you yet. There you go. Simple conversions. Temperature is the next one.
This is my favorite because it's hot, and sometimes it's really cool.
Kind of like Katy Perry.
Well, that's hot and cold.
She's hot. Well, she's
Yeah.
cool too.
She's hot and then cold. And then yes and no.
She's really
Maybe
indecisive.
So. I don't know. Yeah.
Temperature. Oh, that was terrible.
I thought it was pretty good. It's good banter.
So temperature
Banter.
is the kinetic energy, which is speed, kinetic moving, the speed, right? The speed of the molecules is related to the temperature. Literally, if the temperatures are hot, the molecules are moving really, 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 really fast.
And likewise, if the temperature is cold, then the molecules slow down.
Really slow.
So, this slide we see an animation of temperature, and as the temperature goes up, you see the particles are starting to move really, really fast.
Oh, yes it is. And what's that K stand for?
The K stands for Kelvin, named after Lord Kelvin, and it's the SI unit of temperature.
Oh, that's kind of like Celsius and Fahrenheit, but
Yeah.
for nerds.
Right.
For science, yeah.
Indeed.
In science, we use K.
Yeah.
Okay. And there it is. The temperature is now going down. It's getting pretty low there, and you can see that the molecules are actually starting to slow down. And when we get down to the bottom here, it's almost entirely stopped.
Yeah. If they do stop, we've reached a point called absolute zero.
It's 0 Kelvin. And
Yeah.
why is there absolute zero?
It is the point where all molecular motion stops, and it's absolute because you can't go any lower than that. There's no negative motion,
Once
so we have no negative Kelvin.
Once they stop, they stop. We do need to know how to convert between Celsius and Kelvin. Here's the equation. If you have Kelvin, you subtract 273 to get Celsius.
All right, pretty simple. I like that.
For example, 298 Kelvin. Quick, Mr. Giacomo. What's that in Celsius?
Quick. How am I calculating?
3,
Wait.
2, 1.
25.
25
Yes.
degrees Celsius. A
Got it.
simple subtraction problem. Hopefully you didn't need your calculator for that. And some algebra. Do you call this algebra to rearrange the equation?
It's like chemistry algebra.
Okay. Celsius plus 273 will give you Kelvin. For instance, if we had 36 degrees outside, a little trickier going up the other way, what is that in Kelvin? 3,
Can I use a
2,
street shout
no
out?
calculators,
Oh,
1,
no
0.
309.
309 is
Oh,
right
just in the nick of
after the
time.
buzzer.
Oh.
No bonus
Dang
points. So very simple equations you need to know. Is there an equation for Fahrenheit?
Indeed there is, but you don't have to worry about it. That's something that you just do in math class to help to get you to jump through math hoops and whatever. Math hoops.
Math hula
They're like
hoops.
hula hoops. But
So,
mathematical.
so I noticed there's equations for Celsius and Kelvin. Is there an equation for Fahrenheit?
No. Well, yes, but we don't need to worry about it.
Because science doesn't use Fahrenheit.
No, science is too cool for Fahrenheit.
Too cool or
Maybe
hot.
it's too hot.
So there's some temperature conversions. Most importantly, you have temperature and pressure are connected by STP. That means standard temperature and pressure, or normal temperature and pressure.
Right. So this is essentially chemists decide we're going to carry reactions out under some sort of standard conditions, and these are the ones they just decided on. 273 Kelvin, which is
0 degrees Celsius. You
Yeah.
subtract 273. I can do that. 273 minus
that's good,
273,
easy math.
0.
easy math.
And pressure is all that entire list we gave you. 1 atmosphere,
Yeah.
or
760 millimeters of mercury,
there's 1,
or 14.7 psi.
or anything else on that list. When you see STP in a problem, there will be no numbers with it. You need to know that it stands for 0 degrees Celsius and 1 atmosphere.
That means memorize the numbers, basically.
Memorize this slide. You need to know it.
But you'll know the pressures all the time because they'll be on the back of the periodic table.
Yep.
Easy.
You just need to know the temperature. And that's STP, very important. That, in a nutshell, is the kinetic molecular theory.
Fun stuff.